Bismillah Rahman Rahim. In the last video, we have seen the indirect vector control of the induction motor. In the indirect vector control of the induction motor, we determine the cos of theta e and the sine of theta e, which are the unit vectors and are used to convert your current from one frame of reference to the other frame of reference. These unit vectors are computed using theta r, and that is estimated with the help of the information of the speed. So speed is measured and is used for the field oriented control. In this diagram, you can see that we can find out IF and CT with the help of the lambda r and the torque command TE, and from this information we extract or we calculate the slip speed and we calculate the slip angle. That slip angle is used along with the theta t, that is the torque angle of your induction motor, and then the rotor position that is coming through the speed sensor, that is calculated with through the speed sensor. Adding all these together, you determine theta s, that is the position of the stator current phasor in the frame of reference, and then you translate it to the IAS, IBS and the ICS. So we have discussed in detail this block diagram in the last video. The equations which are used to implement this block diagram are shown over here. For the calculation of the IT, the torque component of the current, this equation is used. For the field component of the stator current, this equation is used, and to calculate the slip speed, this equation is used. These parameters are used over here that you can see, and which are extracted from these two commands and are used to set up the reference currents for the inverter control. These currents are given to the inverter control, and the inverter realizes these currents in the induction motor. We can also generate the voltage commands for the inverter control by incorporating the relationship between the currents and the voltages on the stator of your machine in a particular frame of reference. So the phasor diagram that was discussed in the last lecture is very important. With the help of that, you can understand this block diagram. Please refer back to the previous video to understand this block diagram. In today's lecture, we are going to discuss the speed control of the induction motor using indirect field oriented control. So for that, I will start with the help of the induction motor in the arbitrary frame of reference. We have derived this model in detail in the previous lectures. Here you can see the equation in the arbitrary frame of reference representing the induction motor. These are the Q axis and T axis voltage in the arbitrary frame of the stator side, and these are the rotor voltages in the arbitrary frame of reference. Now let's take these two equations, these rows, basically this part will be used for the stator side Q and the D axis voltages. So in the synchronously rotating frame of reference, where the speed is equal to the synchronous speed, so we will be replacing this omega c with omega e, because this is the equivalent circuit in the arbitrary frame of reference. That's why we are representing this speed with omega c, where this omega r is the speed of the rotor. You can translate your motor model in any frame of reference by proper selection of this omega c. In the synchronously rotating frame of reference, omega c is equal to omega e. So you can write down the stator side voltage equations like this. In this, we are going to replace the omega c with the stator speed, right? So this omega e is equal to omega s. So over here, this s is representing the synchronous speed of your machine. So here you can see that we are going to replace omega c with the omega s, or you can also represent it with omega e, and we have set up the equation for the q axis and the d axis of the rotor, right, using these two rows, because these are relating the q axis voltages with the stator and the rotor currents. Now for the field oriented control, as we discussed in the last lecture, the rotor current is linked with the stator current through the coupling coefficient. So the coupling coefficient of the rotor, that is Kr, that is given as Lm over Lr, that gives you the information that how much of the rotor flux is basically linked with the stator. Lm is representing the magnetization inductance or the mutual inductance, that is showing the flux linkages between the stator and the rotor. So if you know that coupling coefficient, so you can estimate the rotor current looking at the stator current, because in the squirrel cage induction machines, it is difficult to measure the rotor current because you do not have access to the rotor winding in the case of the squirrel cage induction machine. Only in the wound rotor type machine, you have the access to the rotor, but that is not used extensively in the industry because of the carbon brushes, slip rings involved at the rotor side. The squirrel cage induction motor is the simplest and the most widely used induction motor in the industry because of its simple structure. But in that we cannot access the rotor side, so we estimate the rotor current using these theoretical equations, those we have set up in the previous lectures. So the rotor current of the squirrel cage induction machine can be estimated looking at the stator current IQS. So now we are going to update these equations, this one and this one, such that these are only dependent on the stator side current, because we can measure that current easily. So we will be replacing these terms IDR, IQR, right, with the help of the this equation, because with the help of this, these currents IQR and the IDR can be represented in terms of the stator current. So using this equation that we derived in the last lecture, in equation 15, we can write down this q axis equation like this, right? So if you simplify this one, perform some simple mathematical steps, so finally you will be getting this equation for the q axis stator voltages, and these are only in terms of the q axis and the d axis stator current. We have eliminated the rotor current using the definitions which we have already defined in the previous lectures, and one of those is this equation. And the second one was the leakage coefficient, that is given by this one, that is equal to 1 minus Lm square over Lr into Ls. Basically, this is equal to 1 minus Kr Ks, where Kr and the Ks are the coupling coefficients of your rotor and the stator. So this is equal to 1 minus Lm over Lr for the rotor and Lm over Ls for the stator. So this can be written as 1 minus Lm square by Lr into Ls. So we have written the q-axis voltage equation in terms of the stator current, and we have used this leakage coupling leakage coefficient in order to simplify the equation, right? So you can develop the stator motor model equations in terms of the stator parameters, because you are only able to measure the stator parameters. Similarly, if you do for the d-axis voltage equation, that is taken from equation 27 from the matrix that I have shown you before, and you update it in terms of the stator current, so you can write down the stator voltage equations in terms of the stator currents only. So let's say this is equation 29. In these two equations, those we have shown seen above, you are using the IDS and the IQS, the d-axis current and the q-axis current. And in the last video, if you remember, we have defined that flux producing component of the stator current is the d-axis component of the stator current in the frame of reference, and that we are going to represent with IF, because it's the flux component, and the torque component is the q-axis component, so we will be representing it with IT. So your stator current has two components, one is along the d-axis, the other one is along the q-axis. The d-axis component is the flux producing component, and the q-axis component is the torque producing component. So we can write down these two equations, equation 28 and equation 29, in terms of IF and the IT, those we have defined over here. So updated equations can be written like that. These are simply the equations in which we have replaced IQS with the IT and the IDS with the IF, so that we can easily understand and visualize them in terms of the torque and the field components. Okay, over here we are going to see one more thing, that lambda r flux linkage is equal to the product of the inductance and the current. So for the rotor side, it will be the product of the magnetization inductance and the field current. And we are going to define that the sigma into Ls is the armature inductance, that is represented as La. So we are going to, you can say, define another variable, that this part now will be considered as La. And the lambda r in terms of the inductance and the field current is given by this expression. So now using this expression in this equation, so this will be updated and will be written like this, right? So over here we are replacing lambda r with the Lm into If. So you will get this equation. And now there are simple mathematical steps. If you go through these ones, so you can represent your q-axis stator voltage equation with the help of this expression. So in this, we have used the basic definitions which we have defined in the previous lecture for the field oriented control. Now, with the help of this one, we can calculate the slip speed, or we can represent this q-axis stator voltages in terms of the slip speed. Why we are interested in that one? Because if you look at the diagram that we were discussing in the last lecture, you need to calculate this theta s using this slip speed. So now in order to correlate these ones, we are going to represent this q-axis voltage in terms of the slip speed. So if you remember the equation for the slip speed, that was equal to this one, that is Lm by Tr into It by lambda r. So lambda r now can be written as Lm into If, as you can see over here, and this equation can be written like this. We know that the synchronous speed omega s or omega e, that is equal to the rotor speed plus the slip speed. This is the electrical speed of your machine, electrical rotor speed. So in terms of the mechanical speed, it can be written like this: P by 2 into omega m plus omega slip. This will give you the synchronous speed. So now using the expression for the rotor speed and the slip speed, that we have seen over here, we can write down the expression for omega e, that is the synchronous speed. So we have already derived it in the equation 22 of the last lecture. So this is the expression for the synchronous speed. Okay. So now this omega e over here in this equation can be written as omega r plus omega slip. So we can modify the voltage equation and we can write it like this. And now we are going to use the expression for omega e that is defined over here, and we are going to update the voltage equation. So that you can see over here, omega slip first of all coming from here, from this set of equation, and we are going to represent in terms of the motor parameters, and finally we are going to get this equation, and if we rearrange this one, we can write it like this, and further rearranging, shifting this term towards this side, we can express it like this, and then finally writing in terms of the torque current it, we can write it like this, right? So it will be equal to vqs minus omega r ls into if divided by rs plus rr by lr into s plus sla. So basically this is this part, right? Okay, so we have derived an expression for the torque current. Basically, we have it over here as well, that you can see from here, that was missing. So it over here, and then you have written the expression for the it, the torque current. So the torque current is given by this expression, and this let's suppose that this part that is rs plus rr by lr into ls, that is equal to ra now, the armature resistance of your machine. So we are going to define another variable over here in order to simplify our expressions, and we are going to call it the armature resistance, that is given by this equation. Okay, now we can write this current equation like this, that it is equal to 1 by ra, taking this common out. So what will be left? 1 plus SLA by RA over here, right? And the R is over here outside, right? So we can write down this equation like this, and finally we can represent it like that. Over here we are going to define that LA by RA is the time constant of our armature circuit. We have already defined LA, and now we have defined RA over here. So the time constant in terms of these two definitions, LA and RA, that is the armature time constant, and we are writing this equation in this form now. So the current equation can be written like this. So over here we have defined another thing, that the gain is equal to 1 by RA, this part. We are going to call it the gain of the armature part, Ka. Right, so this equation, this is Ka 1 by Sta, representing the time constant of your armature, into this Vqs minus omega RLs into If will give you the torque component of the current. Now rearranging this equation over here, we can write it like that It divided by Vqs minus omega RLs If, that is equal to Ka divided by 1 plus Sta. So let's number it equation 24. So we can represent this equation in terms of the control diagram like that VQS is the input, right? And the feedback part is this one, omega R LS into IF. So we have basically this term over here that is linked over here, right? And is being subtracted from the feedback path. So you are going to get the difference of these two, that will be representing this denominator, right? And if it is passed through this transfer function, you are going to get it. So in terms of control diagram, you can represent it like this. From the previous lecture, we know about the expression for the torque. The torque, electromagnetic torque, is given by this expression for the field oriented control, right? So the lambda r is kept. If the lambda r is kept constant, so the whole of this part will be constant, because these are the motor parameters, those are considered as constant. So the torque equation can be written like that, that Kt into It, where Kt is given by this equation if your flux linkages on the rotor side are considered constant, right? So now using this one that we have defined the Kt, this equation, we can also represent it in by using the other definitions, those we have already established, that lambda r is equal to Lm into If. So you can represent your Kt like this. Okay, so what is the purpose of representing it like that? That from the torque component It, torque component of the current It that you are getting at the output from here. You over here you have the VQS. This is coming from the feedback loop. You have the It. So now you can get the torque by using this equation. That if you multiply this torque component of the current with this Kt, you are going to get the torque Te at the output. So we are going to add this part in our control diagram, right? Now let's look at the relationship between the electromagnetic torque Te and the mechanical torque and the load torque of your machine. Okay, so this is the mechanical equation of your induction motor, right? So this is J into d omega m by dt plus B into omega m plus the load torque that should be equal to the torque that is developed by your machine, right? So this is the torque developed by a machine that must be equal to the load torque, the frictional torque, and the torque because of the inertia. So this equation can be written like this. Let me number it equation 37. And now we are going to write it in terms of the electrical speed, because this is the equation representing the mechanical part, and over here we have the mechanical speed, but you know that we have the electrical speed linked with the mechanical speed by the equation P by 2. Theta electrical is P by 2 into theta electrical mechanical, or the electrical speed is equal to P by 2 into mechanical speed. So now using this expression, we can represent this omega m in terms of the electrical speed. So that's why you are going to see this 2 by P over here. Similarly, this omega m in terms of omega r. So you have 2 by P over here. And rearranging this equation, you can write down this one, right? And now taking the Laplace transformation of this equation, so you can represent this equation like this, and finally rearranging, you will be getting this equation, and we can write it like that, that omega r in S domain divided by the P by 2 into T minus TL, that can be written as 1 by Js plus B, where J is the inertia constant of your motor and the B is the frictional coefficient of your motor. So we can also represent it like that, that this is with the subscript m representing the motor part, motor inertia and the motor frictional coefficient. Now incorporating this equation in the control diagram that we were developing, this is the control diagram. So now from we can relate this torque with the speed omega m using this mechanical equation, right? So we have developed that one, that omega r, how it is linked with the Te. So now we are going to add it in the control diagram. So this is the previous part of the control diagram. Now along with that, if you multiply this T by Te with P by 2, so over here you have Te into P by 2, and from that if you are going to subtract P by 2 into TL, that is this part, right? So you are going to get this term over here, and then multiplying it with this term 1 by J m in JMS plus BM, you will be getting the omega r at the output, right? So I can represent this thing like that. This is Jm and this is Bm. So now after passing this term over here, this is the denominator, that is P by 2 into Te minus TL, right? So multiplying it with this transfer function, you are going to get the rotor speed in the S domain, right? Okay, now your this load torque can be written in terms of the load frictional coefficient. You can represent it with that. So let's suppose that P by 2 into this TL, sorry, it should be TL over here, that you are using over here, into that is equal to BL into omega R. Omega R is the motor speed and the BL is the coefficient, frictional coefficient of the load that is connected with your motor. There may be a fan, maybe some other mechanical load. So this is the load frictional constant, and now we can incorporate it over here in our control diagram. Here you can see that we are going to take this omega R, and through the feedback, and what is feedback, that it is multiplied with BL. This will give you this torque P by 2 into TL. So we are incorporating the load torque like that. It is dependent on the speed of your motor. As the speed of your motor will be changing through the friction coefficient, the torque that is being applied in the form of disturbance over your motor, that is going to change, and that is defined like that. So we are going to call this P by 2 into TL equal to this TL, right? So we will be representing it like this now onward. Okay, now we have developed this control diagram. We have defined this over here in the equation 36, and we have seen that what is Ka and Ta we developed in the equation 33, and then we defined this K and Ta in the equation 32 previously, and so on. We have derived all of these things. Okay, now this part over here that you can see, that is equal to omega r into Ls into If. So we have the omega r over here, so we can represent it in the form of the block like that Ls into If will give you this term. So that you can see over here, we are getting this omega r Ls into If from the omega r through this gain block. So there is the inherent feedback of the omega r through this gain, that is basically the back EMF of your machine, you can say, along the Q axis. Okay, now let's update the equation incorporating this load frictional coefficient. So we know that our mechanical equation is given by this expression, that is J into alpha plus Bm into omega, that is equal to P by 2 into T minus TL. So now we can write this Te in terms of the equation that we have seen above, that is equal to Kt into It, and this TL that is equal to BL into omega R, right? So first of all, let me call it this small TL, and then when multiplied with P by 2, it will be the capital one. So we can write down this equation like this, and rearranging, you will be getting this equation. Over here, we are going to say that load plus the motor torque coefficient is now will be represented as Bt, that is the total frictional coefficient of your system, that is equal to Bm plus Bl. So now using this, you can write down this equation like this. Okay, now rearranging it and writing this expression, so you will be getting this equation, and in this equation, this J by Bt, let's suppose that is equal to Tm. This P by 2 into Kt by Bt, we are going to give another name now onwards. It will be represented with Km, and Bt is equal to Bm plus Bl. Now using this equation in these terms, so we are going to replace with this Tm, we are going to represent this with this part with the Km over here. So we have this equation, and now if you take the Laplace transformation of this one, so you are going to get this equation, and rearranging and writing in terms of the transfer function of the speed with respect to the torque component of the current, that is this one. So we can say that if we are going to give the current as an input, it is going to give you the speed as an output. So how they are related? They are related by this transfer function. And what is this Km? This Km is given by this equation. And what is this Tm? Right, Tm is given by this equation. And then you can trace back that what is this Kt and the Bt from the equations those we have set up over here. So we are going to represent the relationship between the speed and the current torque component of the current with the help of this transfer function. Now we are going to assume that we are going to control the speed using the PI controller. So the transfer function of the PI controller is given by this equation, right? 1, 0, and the polarity origin, you can say. And then we will represent our inverter with the help of this transfer function, that it has a certain gain K in, and the time response of your inverter, that is, or the time constant of your inverter, that is represented by the T in. So gain of your inverter is K in, the inverter time response is given by this one, and this is usually equal to 1 by 2 Fs, where Fs is the switching frequency of your inverter. So you give the current command to your inverter control, and then it realizes that current by adjusting the voltage across the machine terminals, or you can say the Q and the D axis component of the voltage. So the inverter transfer function is given by this equation. Right? It varies from application to application. If you have the space vector pulse width modulation based inverter, in that you require the voltages as the reference, so then you will have to translate this IQS in terms of the voltages. Those will be applied as a control command to your inverter, and then it will realize that control voltage at the machine terminals. So it varies from situation to situation, but over here we are assuming that current command is the input, and the voltage will be realized across the machine terminals by the inverter, and this is the transfer function of the inverter. Usually the time response of your inverter is very small because you have the semiconductor switches, so they change the state in a very small interval of time in the range of the nanoseconds or few microseconds. So usually we will be considering only the gain part of the inverter, because the inverter is the fastest component in this loop, because it is based upon the semiconductor and devices. Next, we are going to look at the feedback transfer function, that is equal to HC, that is representing the current sensor. So the response of the current sensor is quite high. It is just measuring the current and mapping it over a certain voltage for the implementation of the control loop. So the transfer function of the current sensor, Hall effect sensor, is simply, you can say, equal to HC, that is a gain of your sensor. And very small delays there because of the current, so we are going to neglect that one in our implementation, and usually we neglect in the drives application. Then we have the speed feedback. We are going to measure the speed with the help of the sensor, so that is a mechanical part that has the certain time response, so that will be considered. So T omega is representing the time constant of the speed filter, and H omega is representing the gain of the speed sensor. So the speed feedback is given by this equation. Okay, now let's look at the control diagram that we have already developed for our induction motor for the Q axis voltage, and how it is linked with the speed omega r to the different motor parameters. Now, how to control this voltage? So in order to control that voltage, we need to insert the inverter in this loop. So here you can see it's the transfer function of the inverter that is added over here, because this VQS will be applied by the inverter, and this will be getting the difference of the error of the currents. We are monitoring the current from here, IT, that has the um, loop transfer function H. This is a transfer function of the current sensor, mapping that current and bringing it down. So this is in terms of the control. Now control command of the torque component of the current, that is the IQS, and the IT sense from here, that is being given to your inverter. This inverter will act as an amplifier and will apply the voltage at the machine terminals to realize the required speed. So we have added the inverter part in this loop. Now along with this, we are going to add the PI controller. Now if you look at this diagram, this is taking the command it, right? So how to get that it? Now we are going to use the PI controller for the speed control. This it is decided based upon the difference in the actual speed and the command speed. So omega r is the command speed. Actual speed is being sensed through this speed filter or the speed sensor, and is being made available over here based upon the speed error, right? That is given to this PI controller. It is mapping or deciding about the torque component of the stator current, and then the error of this one is calculated by looking at the actual current of your machine, and then your inverter amplify, your inverter control is over there, and that takes that information of the error, and then finally decides about what should be the q axis voltage of your stator, and then that is applied and your speed is realized. Okay, now let's simplify this loop. So first of all, I am going to look at this part of your control diagram. This can be simplified and can be represented in the form of the simple block diagram. So we will be simplifying this part now. We have already simplified it in equation 42 above, and now this will be represented like this, that you can see over here, Km by 1 plus Stm, that was relating your it with the omega r. So we are going to replace this loop because we are going to simplify the control diagram. So we are going to represent in the form of the single transfer function Km over 1 plus Stm that relates the it with the omega r. So omega r is over here, it is over here. So this loop can be represented with this one. So your control diagram will be simplified. Now, once you have simplified this one, now you can move back this point from here to here. So if you are going to move it back, so you will have to incorporate this transfer function right over here. So that you can see that if you move this node from here using the basic simplification rules of the control diagram, so you will be getting this control loop now. So in this we have shifted this point from here to here. So you have incorporated the effect of this block over here, right? And now you are getting this loop. Okay, now what is the advantage of that one? Now we can easily simplify. So we are going to represent this loop now like this, and now we can take its equivalent transfer function, and we can replace this part with its equivalent transfer function, and we can simplify the loop. So that is done over here. So this is the forward transfer function, this is the feedback path transfer function HFS. So using this equivalent transfer function of the negative feedback, that is GS over 1 plus GS into HFS, and by using these transfer functions from here in this diagram, you can represent it like this. It's a second order transfer function that is representing the relationship between VQS and the IT, and now we are going to replace this one with its equivalent transfer function. So let's suppose that is equal to PS. So we are going to represent it with the PS, right? So our loop will be simplified. This is PS now, and now that is in series with this inverter part, and we have the feedback H of C in this loop. So now we are going to target this loop now, right? This one, and in that we are going to say this one is the P of S that is evaluated with the help of this expression. Okay, so now we can represent our control diagram like that we have P of S, the inverter part, and the current feedback. So now we can say this current loop can be further simplified and can be represented by a simple transfer function. You know about this P of S, you know about all of these inverter parameters and the feedback path. So now if you look at the equivalent transfer function of this one, so that will be G of S divided by 1 plus G of S into H of S. So the G of S can be obtained by looking at this P of S into this inverter part. So that you can see inverter part multiplied by that P of S divided by 1 plus G of S into H of S, and that will be incorporating this HC as well. So now if you simplify this one, you will be getting this expression, and it's a third order transfer function. So you can use the exact third order transfer function for the design of the speed controller, or you can approximate it with the help of the first order transfer function, because you know that some time constants are very small. For example, this inverter part that is very small, so you can represent this 1 plus s into t inverter nearly equal to 1, because this time constant is very small. But because you have the solid state devices which are operating and which are operated by applying the gate pulses, so you can approximate it with the 1. And similarly, if you have this product 1 plus st and 1 plus st in, so you can represent it like that at 1 plus sta plus t in. Second order part, the s square term can be neglected because this t in is the very small one as compared to your armature time constant that depends upon the armature inductance and the resistance that is usually very large as compared to inverter. So we can approximate this term with this first order term, and we are going to call this Ta plus T in as the TAR. So Ta plus T in is the new definition that will be representing this time constant, right? So with this approximation, we can simplify this one and we can represent it as a first order transfer function. Later on, we will see that what will be the impact of this one. What is the difference between the approximate and the actual with the help of an example. So you will see that there are very small differences there, and we can make this assumption over here, and we can make the simplified expression for the analysis of the for the design of the drive system of the induction motor. So now let's apply these approximations. So first of all, this is 1 plus st in is equal to 1, right? And this part 1 plus sta into 1 plus stm into 1 plus stn, because this will be multiplied with this will be multiplied with this one as well. So this part 1 plus sta into t in from here, in this term and this term now can be written as like that 1 plus sta that you can see over here, and the leftover term is this one. So this part, these three terms product will be written like this into ka plus klm ls if into 1 plus stn. So over here we are going to say that it is equal to 1. So we can write it like this, and then this last term over here. So applying the approximations from this equation A, you are going to get this equation B, and over here you have applied these approximations and you have applied this definition as well, that this Km into If into Ls, right? So this will be called as Kb now onwards, right? So this part Lm, sorry, this is not Km, this is Lm into If into Ls, that is equal to Kb. So let me correct it. This is Lm. Okay, so that's why you can see the Kb over here. Kb into Ka and this term. Okay, now further it can be simplified by making another approximation that we have seen over here, that 1 plus stn can be nearly considered equal to 1 because this time delay is very small. So we can apply this approximation and we can represent our transfer function like this. And now if I take the denominator over here and do some mathematical steps, rearrangements, so we can represent it in terms of the second order equation, that is s square term, s term and the constant term. So rearranging it, you can say over here the coefficient is 1, this is the b term, and this one is the c term. So using the quadratic formula for the solution of this one, you will be having the two roots of this one. So let's suppose that those roots are minus 1 by t1 and minus 1 by t2. These are the two poles in this loop. So those can be determined by using the quadratic formula. And this term TRTM is over here. So taking those ones over here and writing in terms of the equation now, s plus 1 by t1 and s plus 1 by t2 will be equal to this part, and that you have obtained by plugging in the values of the b, c and the a over here, and the simplifying you are going to get this expression. So now what you have over here, you can represent this current loop transfer function, that is the transfer function of this part, this loop, that we are going to call it gi of s. So we are basically computing that one. So gi of s can be written like that using these approximations, right? This is the transfer function for the current loop. And now if we further rearrange it, take the constant terms outside and the 0 and the two poles over here. So Tm is the mechanical time constant, and it is usually very large as compared to your T1 and the T2. And similarly, if you look at this equation A and you look at the parameters of your machine, and if you calculate this T1 and the T2, so one term will be this T1 will be smaller than T2, and both of them will be smaller than the Tm, because Tm is the mechanical time constant. So looking at the relationship between T1 and the T2 and the Tm using this quadratic formula and the motor parameters, so you can say that 1 plus Stm will be nearly equal to Stm. We are going to make another approximation, and 1 plus St2 is nearly equal to St2, and the T1 will be simply considered a constant, because the T1 is the smallest of these three constants. So using these approximation, the transfer function of the current loop now can be approximated like that. Ka, K in, and the T2 and the Tm will be nearly, you can say, cancelling each other. You have only TAR. Why we are cancelling each other? Because they are the higher one as compared to the T1. And then what is this? This is STM, right? We can write it like that, STM. And what is this one? This is can be written as ST2, or you can say this that this term and this term is going to cancel out. Similarly, this T2 will be cancelled over here, and this Tm will be cancelled over here. So you are left with only this part, right? And this term is gone because we have approximated it. So you are only left with 1 plus st1, so that is this one. So you can approximate this transfer function like that. So in this we have this now constant part, so we are going to call it the ki, the gain of this transfer function. And now this t1 is equal to ti, that is the current loop time constant. So we can represent our current loop now with the help of this first order transfer function that we have developed by making certain approximations, right? And this we have already seen before. So now if I mark the points over here, what we are going to get from this control diagram, if I go back and look at over here, over here we have the ITS, that's the input of this transfer function. So let me mark it over here, that this one is the IT, right? And over here is the omega r in this control diagram. And the input of this control loop is, if I go back and observe over here, you can see it's the reference IT that you want to establish, that is IT. So taking it over here, this is the reference IT static, right? So in current loop, and then the PI controller and the sensor. So this is going to now make the loop from the command speed to the actual speed, right? So now you can work out the GH for this one, because now we are going to find out the net transfer function of this one. So this is the forward path, this is the feedback path. So you have G over 1 plus GH in the equivalent transfer function. So GH can be evaluated by taking the product of all of these. So taking the product, looking at the values in these transfer functions, and then using an approximation again that 1 plus STM is nearly equal to STM, because this part is very large as compared to 1. It's the mechanical time constant, so we are going to neglect this part. So this will be approximated at only STM. So using this approximation, the this GH now can be simplified, because this term will be STM, and the this will become S square, and you will be left with this part 1 plus S into T omega I. So over here, what is T omega I? That is equal to Ti plus T omega. So we are going to combine these two together, and we are going to represent a T omega I, another definition. And we are going to define a constant kg as well. This kg is equal to this ki into h of omega, this one, and then divided by the tm, right? That will be coming from here, right? So this is the, you can say, kg, and into ks by ts, that is left over here, and then this s square will be over here, so it will make s square, and 1 plus sts divided by 1 plus st omega I. We have combined this one because this is quite high, and this current loop transfer function is very small. So this 1 plus ti into 1 plus st omega now can be approximated as 1 plus st omega I, the first order term, and in that this ti plus t omega is equal to t omega I. Why we are approximated with the first order? This is large and this is small, so the impact of this term will be very small in this product, so we are going to just consider them with the first order approximation. So making this approximation, you will be getting this transfer function, right? So now you can say that you have this loop that can be represented like this, and in this, if you look at the closed loop transfer function of this part, so you can relate speed with its speed command with the help of this equation, and on you know about all of these coefficients which are being used over here through the approximation. Now, how to decide about the gains of this one? You can use the symmetric optimum function for the zeta equal to 0.707 that is given by this equation. And now if you compare the coefficients, this one with this one, sorry, 3 by 8 into ts square, and then this coefficient with this one, so you can work out the values of the ti and ts and the gain of your controller. So the proportional and the integral gains can be calculated by comparing the coefficients of the denominator polynomial to the coefficients of the symmetric optimum function. This is our symmetric optimum function that gives us the controlled response that's equivalent to the 0.707 damping factor, and with that we are going to consider this equation, that is our actual equation relating our speed with its command. So by comparing these two, you can find out the coefficients by comparing the terms, right? So s square term and the s square term will be compared, s cube term and the s cube term will be compared, and from by the comparison you can say that ts is equal to 6 times t omega I, and the ks is given by this expression. These are the speed controller constants, and the pi gain that is equal to that is given by this set of equations. The kp is equal to ks, that is equal to 4 by 9 into 1 by kg into t omega, that is obtained by the comparison of the symmetric optimum function with the actual transfer function of our machine. And then the integral gain that will be equal to ks over ts as we defined above, that will be equal to 2 by 27 into 1 by kg into t omega I square. So using these two terms, using this symmetric optimum comparison, we can find out the proportional and the integral gain of the speed controller, right? So overshoot is observed in the response of your the speed control, so that can be suppressed by cancelling the zero by the sorry, the overshoot can be suppressed by cancelling the zero with the addition of the pole, that is 1 plus sts, because if you look at this transfer function, that is a zero over here, right? So you can zero this one by introducing another pole 1 at 1 plus sts in the path of the speed command, and you can get rid of the overshoot that is there in the circuit, in the control loop, or in the speed loop. Okay, so now let's look at one example and then we will conclude this lecture. Let's suppose that these motor parameters are given to us, right? And we need to calculate the speed controller constants, and then we are going to verify the assumptions those we have developed in the discussion of the design. So first step is to just simply calculate the parameters those we have discussed above. You have these basic definitions. You can find out the armature constant, then you can find out the Ka that is used in the design, the armature inductance, then the time constant of the armature circuit, then the motor time constant. Looking at the parameters over here, these are given to you, right? So all the parameters are given, and from there you are going to calculate the terms which are used in the design, right? And after calculating these ones, for the approximated current loop, the expression for the Ki and the Ti, as you have seen above, is this one. Ti is simply equal to T1 and the Ki is given as K inverter over Ra. So K inverter you have calculated over here, and you know about Ra over here. So you can find out the approximated current loop parameters. And similarly, based upon this approximation, you can find out the speed controller parameters using the definitions you have seen above. So you can find out the proportional gain, right? So you can also calculate the parameters looking at the exact transfer function. So if you use the exact transfer function, you will have to use this one, and in that this part will be like that. So similarly, for the simplified current loop, you have this expression. For exact speed loop, you have this transfer function, right? So you can compute these transfer function by using these values in the MATLAB by considering the exact loop and the approximated loop, right? So basically, if I go back and explain to you the current loop was of the third order, right? Third order transfer function that you can see over here. Third order transfer function was there, but we have approximated it with the first order transformation by making certain assumption that inverter is very fast. We can approximate 1 plus STN with the 1, and the mechanical time constant is quite large. So you can do approximated calculation, and you can have the exact one. So you can use the MATLAB to simplify this control loop diagram, right? And you can have the exact response, and you can have the approximated response. So the calculations are made over here in this example. And finally, I am going to move at the going to show you these responses which we have obtained, that frequency response of the complete and the simplified current loop. So if you use the exact analysis, you will be getting this one as the response of your system. And if you are going to use the simplified one, so you are going to get this one. So they are very close to each other. So we can make the we can confidently now say that the approximation that we have made to simplify our control loop, current control loop with the first order transfer function, that is a valid one. Similarly, if you compare the speed loop frequency response with and without smoothing and complete and simplified current loops, so here you can see the differences are very small. And what do you mean by the smoothness? That we are going to introduce a pole that is going to cancel the 0 1 plus STS that we have seen the before. So the exact and the simplified or the smoothed methods are giving you nearly the same results, right? So we can apply the approximations, and we can make our expression simpler, and we can make the design steps simpler. Those can be easily and those can be helpful for the calculation of the design parameters by the hand calculation instead of using the softwares. But if you have the MATLAB, and nowadays high computational powers are available, so you can make the exact analysis by looking at this one. So if I conclude this video, we have seen the complete current loop and the speed loop for the design of the drive circuit for our what we say induction motor. So we have seen the speed loop and the current loop, looking at the motor model equations and making certain assumptions. So that's all from this video. I hope that you now will be able to implement this control loop in the MATLAB, and you will have to be able to work out the exact and the approximate response for your induction motor drive, and you will be able to design the speed controller and the current controller for your control loops. So that's all from this video. Thank you very much.